This is a video on Stokes' theorem. The question states, use Stokes' theorem to find the line integral over the curve C of f dot dr, where C is the triangle with vertices 0, 0, 0, 1, 1, 3, and 1, 2, 4, oriented positively. And f of xyz is equal to 2y plus sine of xi plus y minus z squared j plus e to the z k. So first, let's recall what Stokes' theorem says. And what it says is that the line integral over a closed curve C of f dot dr is equal to the surface integral of the curl of the vector field f dotted with n ds. So we need to find the curl of f. So to do that, the curl of f is cross product of kind of like the vector where you're looking at del x, del y, and del z crossed with the f of xyz. So I write down the determinant of the matrix, I, j, k, del x, del y, del z. And then f, the I component, is 2y plus sine x. The j component is y minus z squared. So here's y minus z squared. And the k component is e to the z. So I put e to the z as the final entry of the matrix. Now I find the determinant of this matrix. So to find the I component, I get rid of the row and column corresponding to where the I is, and I get del over del y of e to the z. Well, the derivative with respect to y of something without any y's in it is just 0, minus del over del z of y minus z squared. Del over del z of y is 0. Del over del z of minus z squared is negative 2z. We're subtracting because we're going this way. So the I component is just positive 2z. For the j component, I get rid of its row and column, and I take del over del x of e to the z. There's no x, so that's 0. Minus del over del z of 2y plus sine of x. There's no z in 2y plus sine of x, so that's just 0. So we get 0j, I don't even bother writing it. And then for the k component, I get rid of its row and column. Del over del x of y minus z squared is 0, because there's no x here. Del over del y of 2y plus sine of x is just 2, because the sine of x doesn't have a y, it goes away. And we're subtracting because it's on this side of the diagonal. So I end up getting 2zi minus 2k for the curl of f. Next, I find the normal vector to this triangle. So the way to do that is I find two vectors that lie on the triangle and cross them. Luckily, 0, 0, 0, the origin is a point on this triangle. So I could just take the displacement vector from 0, 0, 0 to 1, 1, 3, and that's just 1, 1, 3 as a vector. And then I cross that with another displacement vector. So I go from 0, 0, 0 to 1, 2, 4, and that's just 1, 2, 4. So the normal vector for this triangle is just 1, 1, 3 cross 1, 2, 4. So then I got to set up the matrix. I have ijk, 1, 1, 3, and 1, 2, 4. I take the cross product. For the I component, I'll get 4 minus 6, which is negative 2, so negative 2i. For the j component, I get 4 minus 3 is 1, and it's always minus with the j component, so minus 1j, or minus j. And for the k component, I get 2 minus 1, which is 1. So that tells me a normal vector to this triangle is negative 2i minus j plus k. So now I can think about the equation of the triangle or the plane where the triangle lies in. And the way normal vectors work is we always know the normal vector dotted with a vector on this plane or this triangle must be 0. And since the origin 0, 0, 0 is on the triangle, the displacement vector from 0, 0, 0 to xyz is just xyz. So now I can just write the normal vector, which is negative 2, negative 1, 1, dotted with the displacement vector, xyz, set that equal to 0. And if I dot that, I get negative 2x minus y plus z equals 0. And solving for z, I get z equals 2x plus y. Next, I can look at the limits of integration. X and y are our variables, so we're really looking in the xy plane. So I can draw the projection of the triangle in three-dimensional space onto the xy plane, which means that you just ignore the z component. So we get 0, 0, 1, 1, and 1, 2. I draw this triangle. Notice that the line that goes from 0, 0 to 1, 1 has equation y equals x. And the line that goes from 0, 0 to 1, 2 is y equals 2x. So I draw my little man to help me with the limits of integration. Notice the man's feet are on x. The man's head is on 2x. The farthest left the little man goes is 0. And the farthest right is 1. So I can write down the double integral. So we get the double integral from 0 to 1 of the integral from x to 2x of, and now the curl of f was equal to 2zi minus 2k, but z was 2x plus y. So I can substitute and write down 2 times parentheses 2x plus y, all times I, minus 2k. There's my curl of f. Then I dot it with NDS. And NDS is equal to 2i minus j plus k dy dx. And there's my integral, my double integral, that represents this original line integral over c of f dot dr. So now the next step is just take the dot product. So I'm going to multiply the 2 through. I get 4x plus 2y. And then I take the dot product. So I multiply that by negative 2. And that gives me negative 8x minus 4y. And then negative 2k dotted with k. That gives me negative 2. So I just have the double integral from 0 to 1, and then x to 2x of negative 8x minus 4y minus 2 dy dx. I could do that by hand, not too difficult, but instead I used a calculator or a computer's calculator. And what I got when I took that double integral was negative 17 thirds. So I can conclude that the line integral over our curve C of f dot dr is negative 17 thirds. And I'm done with the problem. Thank you for watching this video.